Hello, so welcome back to our OneClass channel. Again, my name is Joey. I'm going to be your OneClass chemistry teacher for this session. So what we're doing here at OneClass is that we're going through a kind of journey of verifying and answering solutions asked by frequently asked questions asked by students from all across the world. So what we have here is we compiled basically many questions in kind of the secondary school level. So in secondary school level math and in chemistry, as well as also in the university and college level. What we're doing in this session here is we're going to verify these solutions and I'm going to teach you the concepts behind these solutions so that you have a better understanding of what the material is. So my name is Joey. I'm currently an Ontario school educator and my subjects of interest are mathematics and chemistry as well. So hopefully I'll be qualified by September to teach math as well, which is currently in that process of getting things sorted out. So without further ado, let's get started on today's problems. I have about 10 problems for us in the high school level chemistry kind of portion for today. So we'll get started on those questions. Okay, so what we have first is, here is our first question. So we have lead 2 nitrate and ammonium iodide react to form lead 2 iodide and ammonium nitrate. Let's write this down. And I get some type of equation here. So I get, this is PB. PB, so this is lead nitrate. And they balance it for us, which is nice. And this potassium iodide react to form, this is in aqueous solutions, to form lead iodide, which is a solid. And I have plus 2 NH4 NO3, and this is an aqueous solution. And okay, so let me zoom out for you guys. So you have this kind of chemical equation here. It says asking us what volume of 0.530 NH4I solution, so the ammonium iodide solution, is required to react with 155 milliliters of a 0.580 molars of lead nitrate. So let me write these down here. So I have 0.530 molars, and I want to react it with 155 milliliters of so this here is the concentration. So this here is C, and my my lead nitrate solution is 0.580 molars, and I want 155 milliliters of that. So I want 155 milliliters of that. And I don't know what this is, so I'm going to write this as X or something like that. And I want, again, I have 0.50 molarity of my ammonium iodide solution. I don't know the volume, and I want to solve for the concentration. I want to solve for this volume of ammonium iodide to for the solution first. So this is the first kind of solution. So this is part A, and part B is asking how many moles of lead iodide are formed in this reaction. So that's kind of part B. So it's kind of two kind of questions in this question here. So let's see what they're doing here. So it says here concentration of lead nitrate equals 0.580, which is this, good. So volume, which is 0.155 liters. So they converted this into milliliters, which is good. So let me erase this and I'll put this into liters, which is just simply 155 divided by 1,000. So 0.155 liters. And then we want to calculate the number of moles now, right? Because we know that here is N equals, so C equals N over V. So we know that moles equals concentration times our volume, right? So in order for us to do that, I can simply put N here. I can solve for the concentration, or the moles of lead nitrate here. So that's 0.580 multiplied by 0.155. And we'll see a value of 0.0899 moles. 0.0899 moles. And what we're going to do here is we can actually do a mole-to-mole ratio, right? We can say here that I have, again, one of these guys here is 0.899 moles, but then here I have 2 moles, or the coefficient here is 2, right? So I'm going to have to multiply this by 2 in order for us to satisfy the mole-to-mole ratio. So I'm going to multiply this 0.0899 by 2 to get 0.1798. This is in moles. And once we found this, then we can figure out the concentration, or sorry, the volume of our solution here. So we know that C equals N over V, which is concentration equals moles times, or moles divided by volume, which means our volume is going to equal our moles divided by our concentration, right? And we know that our moles here is 0.1798 moles. I'm solving for this x here, right? Divided by, this is our concentration, which is 0.530 molarity. And I guess I can keep the thing constant, put x because this here is x. Simply throw this into my calculator and we get my value of, this would be I'd get 0.0339. So 0.339 liters, or you could say that this here is approximately 339 milliliters. And this here is my answer for this volume here. So I'm going to erase this. I'll do this in red because it's my answer. So I'm writing 0.339. Sorry, 0.339 liters here, and they should get that as well, which is good. So they got 0.339, which is about 339 milliliters, which is correct. So this solution, the part A is correct here, which is great. And what we want to do now is we want to find how many moles of PBI are formed in this reaction. So I want PBI here, and let me just draw a line between the products and the reactants here. I'm going to erase this guy here, just to draw a line here, and this was 0.1798 moles. So again, PBI here, again, I don't have a coefficient here, so it's a 1-to-1 ratio with the lead nitrate here. So it means my moles here is going to be 0.0899 moles. And this here will be the number of moles that are being formed as well. So again, I want how many moles of PBI are formed in this reaction. Well, I know that it's going to be 0.0899 moles, which are formed right in this reaction here. Because again, the coefficient here is 1, and it's simply a 1-to-1 ratio. So in this case here, it's 0.0899, and I should have written this in red because this here is my answer. This here is 0.0899 moles. So these two are my solutions. Again, A here is 0.339 liters are needed, and I also form 0.0899 moles of lead iodide. So this solution here is correct. Again, they have this answer, which is given here, and also here as well. So the solution here is correct. It's good analysis as well. Ooh, okay. Number 2. I have a lot of these guys here. Holy crap. Okay, let's see. I might just go and break this down into kind of problems here, but I have 2. So this is classify each substance as strong acid, strong base, weak acid, or weak base. So my first guys here, HBr, or let me I guess I'll just write these down and then I'll go through it as well. So HBr, I have hydrobromic acid. This is a strong acid because this associates into, this guy associates fully into, if I add H2O, dissociate fully, it's not in equilibrium. I'm going to get Br minus and H3O plus. So my hydronium ion and Br minus. So therefore, this guy here is a strong acid. The same thing applies for HCl, is also a strong acid because of this reaction here. It's going to dissociate fully. I can get my hydronium ion and my chloride ion, and it's also a strong acid. And exactly the same thing for HNO3, which is nitric acid. This here is also my strong acid because I know it dissociates fully. Strong acid. HCl4 is now different. So the reason why is HCl4 is different because if I write down HCl4 here, and if I do the reaction here, this here is, this here is perchloric acid. If I add water to this, this is actually not going to dissociate fully. It's going to be in equilibrium, and I'm going to form my H3O plus because it's an acid here, and I have my ClO4 minus here, which is my perchlorate ion. And this here, this is actually a weak acid because it does not dissociate fully. So that's HCl4. Let me just check my answers. Let's check my answers here. So it says here, oh, they put it in, I don't know what order they put it in, but HBr is strong acid, which is good. HCl was here a strong acid, that's good. HNO3 is also strong acid, that's good. And HClO4 should be a weak acid. HCl4. Where do I see this? HCl4. I don't think they put it here. They put HCl3 minus, but I don't think they put HCl4. Weird. Okay, but this one we know it's a weak acid, so I don't think they included it in the solution here. But this is a weak acid, and I don't think they verified here, which is okay. HNO2 is different. So HNO2 here is going to be a weak acid, and the reason why is because of the second dissociation. So I have HNO2 plus H2O. This will be in equilibrium with, again, I have H3O plus, in this case I have here this NO2 minus, and this here is a weak acid, and this is nitrous acid here is a weak acid. Nitric acid is a strong acid. Nitrous acid is going to be a weak acid here. So this guy here is a weak acid, which is good, and that's what they got here. H2CO3 is kind of my next guy here. And again, basically the concept of this here is, what I'm doing here is I'm just writing out the equilibrium reaction, right? And seeing whether or not it dissociates fully or does it not dissociate fully here. So again, I have H2CO3, I'm going to add H2O to it. It should be in an equilibrium, and I'm going to remove a hydrogen here. So I have HCO3 minus plus H3O plus here. And this here will be a weak acid. So HCO3, let's see here, what is H2CO3? Did they include that as well? I don't think they included it in this problem here. Yeah, I don't think they included the H2CO3 here. So this was missing, and the HCl4 is missing, right? So let me just write this down first. HCl4, and this is H2CO3. And then, okay, next is HCOOH and C2H5COH. Both of these guys are weak acids because they're organic acids. So the rule is basically with an organic acid, such as this here is methanoic acid. This guy here would be propanoic acid. These guys here are organic acids, so therefore they're always weak acids. So 1, 2 is a weak acid. C5H5N here would be a weak base, and the reason why that is that, and I don't think they included it here as well, and it's because it's an amine, and organic amines are usually weak bases. So maybe I'll write this down here. So I have C5H5N. I'm going to add that with H2O, and this is going to I'm going to create this would be C5H6N plus, or actually I wouldn't write the 6 here, I would write 5 and I write NH here, and this would be plus OH minus here, and this guy would represent a weak base, and I don't think they wrote that here as well. So I'm gonna C5H5N here as well. Lithium hydroxide and sodium hydroxide are obviously strong bases, same with calcium hydroxide and potassium hydroxide, so they believe they included that here. Yeah, these are strong bases because of the hydroxide, so strong bases, not strong acids, sorry. Lithium hydroxide, sodium hydroxide, calcium hydroxide, and potassium hydroxides are all strong bases here. And finally, I have, this is methylamine, which is going to be a weak base. So I have CH3 and H2. I can add that with H2O, and I'm going to get in equilibrium, I will get CH3 and H3 plus OH minus here, which proves that this here will be a weak base because I'm creating this hydroxide ion here. So let's see. Or they wrote here weak acid actually. Let's see. Methylamine should be a base here. So I don't know why they wrote a weak acid here. That is not correct. This solution here is not correct. So let's see. CH3, NH3 here, yeah. So this here is not, actually not a, not a weak acid here. So solution, I'm gonna say solution here is incorrect because they're missing a lot of stuff. So solution is partially correct. Missing the following terms. Following compounds in answer. So HCl4, I said it was a weak acid. This guy here is a weak base. This guy here is also a weak base. And I wrote that CH3NH2 is a base, not a weak acid. And I'm going to write down the formula here. So CH3NH2 plus H2O is in equilibrium with CH3 and H3 plus OH minus. So right, therefore, CH3NH2 is a weak base. Okay. So I'm going to say solution is partially correct. They're missing some answers. So I'm just going to say solution here is incorrect just so I can check this answer for them as well. All right. Next, I have a, this is provided IUPAC name for the structure shown. And I want the structure shown for this guy as well. Okay, so I'm going to have to redraw this basically because we're mostly familiar with kind of line diagrams. So I'm going to have to redraw this. And hopefully I redraw this correctly because it's going to depend on my naming here. So what do I have? I have, let's see. I have a CH3. H3C. I'm looking from the top down. I have another, and it's going to be bonded to a CH2, I believe. So this here is a CH2. Bonded to a CH2, which is also bonded to another CH2 here. Or I think that's a CH actually. Sorry, CH. This is bonded to CH2. Bonded to CH3. And then from the CH, it's going to be bonded to a CH2. Yes, this is a CH2. This is another CH2. And this here is going to be triple bonded. Or no, this is going to bond to a carbon, which is then triple bonded to another carbon. And that's going to bond it with a, it's going to be bonded with a carbon here. I believe this is CH2 and then another CH3, I believe. So I count 1, 2, 3, 4, 5. So I'm thinking it's CH2 and then CH3. Bond CH3 here. And let me just check to see if that's correct here. And I believe it's correct, right? So I have my solution here. So I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's good. 6, 7, 6, 7, 8, 9, 10, 11. So that's good. Okay. So I have this kind of structure here, and let me name this structure here. So what I'm going to do is I'm going to first, if I want to name the structure, I'm going to minimize the number of I want to find the longest chain and minimize the number on this triple bond here, right? Because this triple bond is very, very important. So I would actually count from bottom to top here to minimize the number. So I'm going to go, this here is 1, 2, 3, 4, 5, 6, 7. And I can either go 8, 9 or 8, 9. It doesn't really matter in this case. I'll just go 8, 9 in this case. So, and then my functional group is I have an ethyl group 1 and 2 on 7, right? So I can say my naming here would be, I'll write this in blue. This would be 7 ethyl. 7 ethyl. And then my longest chain here is non, right? So I have non. And then my triple bond here is on carbon 3. So non 3 and then Y and E here. So 7 ethyl, non 3 ine is going to be my answer for the solution. And as you can see, 7 ethyl non 3 ine here is also correct. So this number 1 is good. And let's look at the second solution here, or second question. So I'm going to redraw this. So I have a CH3. I'm starting from here, and then I have it's bonded to a CH2, bonded to another. This would be a CH2. And it's going to go down, bond to another CH2, bond to a carbon. This is triple bonded to a CH group here. Bonded. This is bonded to a CH2. This bond to CH3, and this guy's also CH3. So how would I count this kind of structure here? Again, I have a triple bond here, right? So I want to place priority on this triple bond here. So I'm going to start from basically here. So I have 1, 2, 3, and then I can either go 4, 5, and 6, or 4 and 5 here. So I always have to pick the longest chain here. So in this case, I'm going to go 4, 5, and 6 here. Because again, if I went 4 and 5 here, it wouldn't make sense here. And again, on 3 here, I have a methyl group here. So this here is a methyl group. And on 3 this is an ethyl group as well here. So this here is a methyl. And this here would be a ethyl. So what I can say here with my IUPAC naming, I can say that this structure is going to be, I have, on carbon 3, I have 1 methyl. 1 methyl. I have, on 3, I have 3, sorry, it's going to be 3 ethyl. And 3 methyl. 3 ethyl, 3 methyl, or you could just say that this is simply isopropyl, but you don't have to worry about that in terms of our naming. So 3 ethyl, 3 methyl, and then we have 1, 2, 3, 4, 5, 6. So we can say that there's hex, and then it's going. Our triple bond here is a 1, so hex 1 ion here, or you can just write hex 9 to insinuate that the 1 is on the triple bond is on carbon 1 here. So 3 ethyl, 3 methyl, hex 1 ion is our answer, or you could say 3 isopropyl. Hex 1 ion. So either one works. This one's the IUPAC naming, and the isopropyl is kind of the common name here. So this either works. So this works, or you could write 3 isopropyl, and then the hex 1 ion. So either one works. Either one is correct in this case. And as you can see, they did 3 isopropyl hex 1 ion. So the solution here is correct. Good analysis here. Okay, that's number 3. Number 4 is like a bunch of questions in one here. So it's number 4. And I don't know if they actually answered all of them. So let me just check the solution, because this is like five all questions here. Okay, so they only answered actually the first one here, which is fine. So I'm only going to answer the first one here. It's asking you to write the equation for the decomposition of sulfurous acid. So first we have to figure out what is sulfuric acid. So in this case, we know it's an oxy acid, right? So it's made up of, let's see, I know sulfuric acid is H2SO4. This here is sulfuric acid. So sulfurous acid would be H2 SO3, right? It'll be it's one less oxygen in sulfurous acid here. So H2SO3 here would be sulfurous acid. Sulfurous acid. So this here is what I'm looking for. H2SO3, and I want to write the decomposition here. So when we talk about decomposition, so I have H2SO3. This is an acid, so I write AQ here. It's going to dissociate or decompose to form. So what am I forming in this case? Well, I'm forming basically, it's one decomposition reaction. It's a one kind of reactant to basically 2 or more products here. So you can say here that with H2SO3 can basically dissociate into, I have H2 gas. Again, this here is H2, and it can have the SO3 minus, or this is the sulfite ion here, right? So this here is, or this here would be an answer here. And this here is also an answer here, because they have, it's decomposing to form sulfur dioxide and water as well. So this here is also an answer as well. So it depends on how it decomposes, and we don't know how it decomposes in this case. So we're going to say that this is going to give us SO2, which is sulfur dioxide. SO2 is in a gas form, and I'm going to get H2O, which is a liquid form here. So this here is our solution for this problem, and this here is also a good solution as well. Again, we don't really know how this decomposes, depending on, you can think of it as like these 2 blocks. You can think of it as like this block here, which is SO3, and then it's decomposing, so it forms some type of gas, right? So we know that sulfur dioxide is gas, so you can say it's SO2, and the other oxygen is simply just going to stick with this H2 here to form water. So you can think of it as kind of 2 blocks here. And you have to, basically the logic here is that SO2 is a gas. So this is sulfur dioxide. So this here is a decomposition of sulfuric acid here. So the solution here is correct. Basically, the other solutions here, they're asking for double displacement reactions with the solubility table, predict whether or not this would exist. So you have to actually figure out, you have to get a solubility table and write this down. But again, no solutions written here, so I'm just going to say for solution, I'm going to say solution is correct. It's a good analysis as well. Okay, number 5. What is the hybridization in CO2? So, hybridization of CO2. So first, what I would do is I want to draw the structure of CO2, right? So I have here the carbon in the middle, and I have 2 oxygens. And in order for me to complete this, I need to make, again, carbon make 4 bonds, right? So I'm going to have a double bond on one oxygen and double bond on the other oxygen here. And as you can see, this here is linear, right? I have a linear type of molecule here. If you were to check this on Vesper theory, so again, I have a Vesper diagram here. As you can see, CO2 here would make it linear, right? This example is CO2. I have AX2 here, and it would actually make it sp hybridized. And how do we know that this is sp hybridized? And that's actually our answer for this problem as well. If you're not given our Vesper theory, how do we know it's sp hybridized? Well, what we have to do first is we have to list basically the types of hybridization first. So most commonly we have sp3, we have sp2, and then we have sp. So in sp3, a good example of sp3 here is CH4, right? CH4 is sp3 hybridized, is going to give us a tetrahedral shape. sp2 is kind of if I had one double bond in sp2, I would get an sp2 hybridization. If I have one double bond here, I'm forming one pi bond, right? In this case, tetrahedral, I have all sigma bonds here. In sp2, let me find an example of sp2 here. sp2 would be something like a bent structure here. So I can say maybe a trigonal planar, for example. The AlBr3 here would be a great example of sp2. AlBr3. This is a trigonal planar. And this here in sp2, I have one pi bond, and the rest are sigma bonds. I have one pi bond here. And in trigonal planar, again, AlBr3 here, the lone pair it contains my pi bond, right? And then finally in sp, I have CO2. This would be a linear shape. I'm forming 2 pi bonds, and the rest are sigma bonds here. So sp here, again, I have 2 double bonds here, right? So this here is one pi bond, and this here is the other pi bond here. So therefore, it's going to be sp hybridized here. So in this case, let's see, sp hybridized. So it's going to have, the carbon atom has sp hybridization, the O has sp2 hybridization. So this is good. This is, again, I'm talking about the carbon here. Like, this carbon is sp hybridized, but the oxygens here will have sp2 hybridization, right? So this here would be sp hybridized. Carbon here is sp. Oxygens here are sp2 because it only contains one double bond, right? So both oxygens here are sp2 hybridized, but the entire molecule would be sp hybridized. So that's a trick here. So this here, these are all separate units here. However, if I said what is CO2, well, I know it's sp hybridized here. So this here is the correct solution. So the solution is correct. We can also conclude that CO2 is a sp hybridized molecule. It's the molecule due to its linear geometry according to Vesper theory. So the solution here is correct. Number 6. how many liters of water are required to dissolve 1 gram of barium chromate at 25 degrees Celsius. Molar solubility of barium chromate is 1.10. Okay, so number 6. Yep. So I want to first figure out what is the formula of barium chromate. So I know that barium is Ba here. Barium, this is Ba. It has a 2+ charge. Ba is a 2+, and chromate is actually a polyatomic. So chromate, I know that it's CrO4, and it also has a 2- charge here. It's one of those polyatomic guys here. So barium chromate would be, my chemical formula is BaCrO4. And this here is my chemical formula for barium chromate. And I want how many liters of water are required to dissolve 1 gram of barium chromate here. So in order for me to do this, I need to figure out the molar solubility of barium chromate first. So I need to find the KSP of barium chromate. So let me Google that. And I will get at KSP at 25 degrees. So this is KSP would be 1.17 times 10 to the negative 10. And this here says barium chromate in water is 1.1 times 10 to the negative 5. So I don't know where they're getting this kind of KSP value, but I think their KSP value is wrong already. I'm taking my KSP table from this guy here. So if you look at our kind of KSP solubility product constants here, we're looking at barium chromate here. So barium chromate is this guy here. It's 1.2 times 10 to the negative 10 here. And they should give you this in your test here. So immediately this answer is already wrong, because molar solubility here is already wrong here. So in this case, I have this KSP value here, and what I want to do now is I want to convert this grams into moles, right? So I have 1 gram of barium chromate, and then I have also the molar mass. I have to find the molar mass of barium chromate, right? So let me figure that out for you. So this here, I want moles equals mass over molar mass. The moles is going to equal 1 gram divided by our molar mass of barium chromate, which is, let's see, Ba has a molar has 137.33 as our molar mass here. So it's 137.233 plus our molar mass of chromium, which is 51.996, plus 4 times our oxygen here, which is 15.999, right? So this will equal, take out my calculator, 1 divided by 137.33 plus 51.996 plus 4 times 15.999. This is going to equal 3.94 times 10 to the negative 3 here. So let's see. Let's see if they got moles here. I don't even think they got moles here, actually. So I don't know if they got the question right. So it's here, I would have gotten 3.95 times 10 to the negative 3 moles. And now I have the moles of barium chromate. What I can do now is I can figure out using my, write down my KSP kind of value here, right? So what I can do here is I can, let's see, I want the volume, right? Okay, so I have 3.95 times 10 to the negative 3 moles, and I'm just trying to check their solution here. It's kind of weird. It says take the KSP value and divide it by the molar mass of barium chromate, but they're multiplying the barium. But so this doesn't really make sense here. So it says take 1 gram. Okay, so I have 2.787 times 10 to the negative 3 grams per liter. So this is the density of this, actually, grams per liter. And I want to figure out how many liters of water. This is 2.78 ppm here. I don't know what they're trying to solve here. So the solution is definitely incorrect here. I'm just figuring out where they went wrong here. Let's see. So what I can do is, if I want to actually solve this problem by myself, I can basically write down the chemical reaction, right? So BaCrO4 is going to dissociate into Ba plus, or Ba2 plus, and CrO4 2 minus here, right? And I know the moles of this is 3.95 times 10 to the negative 3 moles. And what I want to do is I want to find the molar solubility. Oh, the molar solubility is 1.10 actually. So, or it's 1.10 times, I think it's 1.10 times 10 to the negative something. And I think that's what they were trying to solve for here. But I think it's cut off or something, so they didn't actually give me the answer here. Let's see. So they have 1.1 times 10 to the negative 5 moles per liter. This is our molarity. Is this what? Oh, I think this is what this is actually. So they actually give you the concentration, which is 1.10 times 10 to the negative 5. Okay. I think I know what they're doing here now. So this here is our moles. It's very, very hard when like stuff like this gets like cut out. It's very, very hard for me to actually decipher what they're trying to do here. So 1.1 times 10 to the negative 5 molarity. And then I'm going to multiply it by, or can divide it by our moles here to figure out what our volume is going to be here, right? So here's volume. So I know that, again, N equals C over V, or sorry, C equals N over V. So if I want to calculate my volume, it's going to be moles divided by our concentration. So I have 3.95 times 10 to the negative 3 divided by this 1.10 times 10 to the negative 5. It's going to give me the volume, which is 359. 359 liters here. And as you can see, this here answer in liters to 3 significant digits is 359. So I will round it to 359 liters. So this solution here is correct. 359 here is correct, and I believe they have 359 as well. So this solution is correct, but the question was cut off, so I couldn't actually see what it's 1.1 times 10 to the negative 5 is our kind of answer here. So I'm going to say solution is correct. Question was mislead. Question is missing information here. Missing information. And I'm going to say, so basically molar solubility of barium chromate is 1.10 times 10 to the negative 5 here, and then we can solve it here. And let me just write this down here, so I can say moles of barium chromate would equal 1 gram divided by the molar mass here, which is 137.33 grams per mole plus 51.996 grams per mole plus 4 times 15.999 grams per mole, which would equal 3.95 times 10 to the negative 3 moles of barium chromate. We say volume of barium chromate would be equal to moles of barium chromate divided by our concentration, or molar solubility. Which will equal, copy and paste this guy here, divided by our molar solubility, which is 1.10 times 10 to the negative 5 m, which would give us our volume, which is 359. Therefore, we would need 359 liters of water to dissolve 1 gram of barium chromate. So there's a solution that's correct, but they just had it really, really poorly outlined here. Okay, let's look at, this is number 7. Calculate the delta H of the combustion of glucose using delta H F naught values. Calculate the delta H F naught value of glucose to be used in the above using the following information. Must be calculated and not be looked up. Please show all steps. Okay, so this is number 7. So 6 CO2 plus 6 H2O. Okay, this is way too big already. Six CO2 plus 6 H2O give us C6 H12 O6 solid plus 6 O2 gas. The delta H here is 282 kJ. It's asking us to calculate delta H reaction of glucose using HF naught values. So basically what they have here is we want basically the standard heat of formations, and they can all be found in the table, and I'm not given actually the table here. But what we know from this reaction here is this is actually not the combustion reaction. Combustion reaction is actually the reverse, right? So I'm going to actually have to rewrite this in terms of the reversed reaction here. So C6H12O6 solid plus 6O2 gas, reactive form this guy here plus 6H2O liquid, and the delta H of this reaction is simply just flipped, right? So this is negative 2826 kJ here. So let's see. So they want the kilojoules per mole here, right? So we want to figure out how many moles here are given here. So we have to find out the standard heat of formation. So I'm not given this table, so I'm just simply going to look at this table here. So for CO2, it's negative 393.5, and then so on and so forth. So what I can do now is I can figure out the, if I have the standard heat of formations, I can actually use Hess's law to figure out our enthalpy of reaction, right? So let me figure this out first. So let's see. I guess I don't have to flip this equation here because it says calculate delta H of F naught of glucose. So not the heat of reaction here. So yeah. So I actually don't need the reverse reaction here. I thought they wanted the delta H of reaction. So I basically use Hess's law here, which states that delta H of reaction equals basically the sum of products of delta H of our products, H products, minus the sum of all delta H's of our reactants here. And this means this would equal, so products here, I'm making C6H12O6 and 6O2, right? So in this case here, I don't know what this glucose is. So I can say this is simply just our X value here. And so I'm going to multiply by 1 because 1 is our coefficient here. I'm going to add, again, the product here, which is 6. I have 6 oxygens, and O2 here is simply just 0, right? Because again, this is an elemental compound here. So this is simply just 0 kilojoules per mole, minus the sum of all the enthalpy of our reactants here. So I'm going to have 6 carbon dioxides here, which is negative 393.5. So negative 393.5 kilojoules per mole. Plus, and again, this here is our delta H of products, and this guy here is the reactants. So I have 6, and then I have 6 more of, let's see, I have 6 CO2, I have 6 H2Os, and H2O has negative 285.8 as this delta H of formation here. So negative 285.8 kilojoules per mole. And then I'm going to zoom out here for a sec so you can see everything here. So this simplifies to, again, this is here is 0. So I simply have x here, x minus, and then I have here, this is negative, this is minus, I can distribute these guys here. So minus, I have 6 times this, negative 393.5. So let me just use my calculator, 393.5. So give me negative 2361 kilojoules per mole plus, so whatever 6 times negative 285.8 is, it's going to give me negative, this is their minus sign here, minus 1714.8 times kilojoules per mole. So equal x minus, and I can subtract both of these guys here, right? So I have negative 2361 minus 1714.8, give me a value of negative 4075.8 kilojoules per mole. The negatives cancel out, so I have x plus 4075.8 kilojoules per mole here. And this here, I know that delta H of my reaction, I'm given that, right? Delta H of reaction is 2826 kilojoules, right? So I can say this guy here, delta H of reaction is simply 2826 kilojoules. And now what I can solve for is I can solve for my x value here, right? So I can move this guy to the other side. I can move this to, I can subtract both sides. So I have x here is going to equal 2826 minus 4075.5 kilojoules per mole. In this case, I'm assuming that there's 1 mole of in this solution here. So I'm assuming that this here is also kilojoules per mole. So I'm assuming 1 mole here. So that's why the units work out here. So I have 2826 minus 407.8. So 2826 minus 407.8, which give me a value of negative 1249.8, which is our answer. So the solution here is correct. 249.8 kilojoules per mole here. So the solution here is correct. Good analysis as well. Okay, that's good. Let's look at, that was number 7. Let's look at number 8 and finish off with number 8 here. It says rank the following fatty acids from highest melting point to lowest melting point. Which of the following statements are true? Okay. So let's see number 8 here. So I want to rank them from highest to lowest melting point. To lowest MP. And then I have these compounds here. So I have CH3, CH2, 7, CH2, 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 2, 7 COOH. I have CH3, CH2, 10 COOH. And then basically all of these guys here. Okay, so how do I figure out the highest melting point and lowest melting point? We'll have to look at the intermolecular forces, right? In this case here, they're all carboxylic acids because they're all fatty acids, which is good. But some of them have double bonds and some of them don't have double bonds. So for example, this guy here is a long chain alkane. This one here is also alkane here, but they don't have a double bond here as well. So in this case, they would have, you can think of it as a saturated, it's a saturated kind of fatty acid, and these double bonds here are a non-saturated acids here. So in this case, melting points as follows, and they actually give us the numbers here, but again, I don't know the numbers, right? And again, the melting point, the highest guy here is CH3, CH2, 14, which is correct, right? Because this here is stating that alkanes, again, have a higher melting point than alkenes do. So I'm saying that CH3, CH2, 14, COOH is going to be the highest melting point because it's a straight chain alkane. Next is going to be a second longest straight chain alkane, which is CH3, CH2, 10 COOH. And then I'm going to compare the alkenes together, and it depends on the size of the alkene. In this case, I have this here is a 7, and this is a 7, a 4, and a 4. So this is going to be the next guy here. So CH3, CH2, 7, it will be the third highest. So like so, CH3, CH2, 7. So that's what this is. And then finally, it's the last guy here. So this, so they ranked it correctly here, which is good. So I'm gonna write down CH3, CH2 7, CH double bond CH, CH2 7, COOH. And the reason why the reason why this is the highest MP is this here is a straight chain. This part, they're all carboxylic acid, so we don't have to worry about that part. But this here is our longest alkane chain. This here is the second longest. And this here is our longest alkene. And therefore the other structure here is going to be the last guy here, which is CH3, CH2 4, CH double bond, CH2 4, CH2 2, COH, whatever. So this here is the shortest alkene chain. Shortest alkene. So basically, when we talk about highest and lowest MP, we're talking about the intermolecular forces. When we have intermolecular forces, we have hydrogen bonding because of the carboxylic acids. We also have dipole-dipole because of the electronegativity difference between carbon and oxygen. But in this case here, we care about the London dispersion forces because they are such big molecules, right? So we care about the longest alkane and then the shortest alkene, and that's how we're going to rank these guys from highest to lowest melting points. And again, it says which of the following four statements are true. So we're saying a saturated fatty acid with a greater molecular weight has a higher melting point than a saturated fatty acid with a lower molecular weight. So this guy is true because the higher the molecular weight, the higher the melting point. The stronger the London dispersion forces. So number A is correct. A is correct here. B, it says a saturated fatty acid with a greater molecular weight has a lower melting point. This here is false because it has a higher melting point than a saturated fatty acid with a lower molecular weight. And then C here says a saturated fatty acid has a higher melting point than an unsaturated. It was true because alkanes are higher melting point than alkenes, and which makes D false, right? So saturated fatty acid has a lower melting point. This here is false because it's higher in melting point. So A and C are true. Let's see. So it says unsaturated have lower melting points. That's true because of the molecular geometries. Again, tetrahedral bond angles for saturated fatty acids is relatively linear. So they're stacked together, which is good. And again, with double bonds, there are actually kinks in the hydrocarbons, so they don't stack as well. So the intermolecular forces are indeed weaker. So this solution here is correct. Solution is correct. Good analysis. I'm going to say here that statement 1 and 3 are true, and the statements 2 and 4 are false. And the reason why is that we can say saturated fatty acids have a higher melting point than unsaturated fatty acids because saturated fatty acids, alkanes, can stack on top of each other easily, making London dispersion forces. Therefore, its dispersion forces, or actually, turns out, which makes it harder to break up. And then we can say saturated fatty acids with a higher molecular weight have a higher MP than saturated fatty acids with a lower MP because they have higher London dispersion forces, which makes harder to break up. So the solution here is correct. Good analysis as well. So again, thank you so much for watching. That was question number 8. I'm going to save the last 2 questions for the next stream, probably on Thursday. Again, thank you so much for watching. My name is Joey. I'm a teacher at OneClass. If you like these channels or these videos, again, check out our YouTube channel at youtube.com/OneClass. You'll be able to find all our videos and all our live streams that are posted on the website. Again, thank you so much for watching. Stay safe, stay healthy. Have a great day. Take care.